Thanks, everyone. Welcome to this virtual seminar. Okay, our speaker today is Josh Priest. Okay, Josh received his bachelor's degree in computer science from UVA in 2019, December of 2019. He's been with us since the summer of 2019 when he worked with me and Madhav for a project that was part of the summer program. Josh is going to tell us about the EoN++ system that he has implemented, which is an extension to EoN. This work was supervised mainly by Chris Kuhlman. I understand that the expansion of EoN can also be pronounced as Epidemic Sonnet Works, okay? But what Josh is going to tell us, okay, because this thing includes a demo, is much more than a sonnet. Okay? So Josh, the floor is yours.
Thank you very much. All right, so like Ravi said, I'm going to be talking about what we're affectionately calling EoN++, which is a set of extensions and modifications to the Epidemics on Networks system. So to give people some background in case you don't know what the Epidemics on Networks is, it is a Python library that's built on top of NetworkX, and it's designed for contagion simulations. It focuses on a limited set of contagions, mostly SIR, SIS, and Gillespie models. And all of the models run in continuous time. Each time step is when it calculates the next node changing state. It's not discrete where a time step will evolve one at a time, so time one, time two. And it's a Python library, so all the code, if you're wanting to run a different simulation, you need to write code for each different one. So if you make any major changes, you're going to need to write code for a new simulation. I took the Epidemics on Networks library and made some modifications to it. So I changed it from continuous time to discrete time, which is more desirable because you can kind of investigate how simulations are looking like at certain time steps. I added some transition rules, which I'll expand more upon later, but these are pretty common transition types, discrete as like a exact amount of time that a node might remain in the state, a probabilistic transition where an agent has a percentage chance to change state at every time step, threshold models where an agent might change state if a certain number of neighbors are infectious. And so with these transition rules, we can build models that can expand over all sorts of different things, including but not limited to the SIR, SAS, and Gillespie type models that EoN supports. In addition to this, there's a scheme of heterogeneity where each node can be assigned a different model. And this kind of allows very complex simulations where part of your network might be a threshold, agents with a threshold model, and part of it might be a probabilistic type. In addition, the EoN was restricted to certain exact state sets. So for example, SIR is limited to exactly state S, I, and R. EoN++ is not limited by that. There can be any number of states named whatever you want, letters, numbers, names, and they can all be supported in a single simulation. And finally, this will accept directed and undirected graphs. EoN, I believe, defaulted to directed graphs, but EoN++ has support for both. I also added some additional features. So with EoN++, we can support multiple models, graphs, and initial state sets in a single invocation. So if you want to run a very large set of simulations going over multiple different graphs and different seed sets, that's entirely possible. We can specify the random number generator seed. This is very important for getting consistency among results over several different runs. Very big is there's no need to write any code. All of the input is handled via input files. So for most instances, no code should be written at all. It's limited just by how creative you can be with your input files. And finally, it runs anywhere, including Ribana. That's pretty expected. Kind of as a high level display of what's going on here, the EoN++ system is separated into 3 distinct modules. The first and kind of the most complex one is the contagion simulation module. This is where kind of the meat of the calculations are done. So you take in the models, the graphs, the initial states, the transition rules, and any parameters you might have additional to that. And that will get your simulation done and spit out some very raw output. This gets fed into a data analysis module, which lets you kind of select important data that you're interested in and processes it into a kind of more readable output. And that can get fed into the plotting module, which can produce some reasonably pretty plots with certain parameters. So I'll go deeper into each of these in the future, starting with the contagion simulation model. But first, I'll comment a little bit on the parameters here. So each module takes in a configuration file in order to get the parameters in. And so they're in a pretty readable and commented format, but a small example is a file like this. It has a header and some text names that can be set to file names or numbers or parameters, whatever is needed. And so all of these will be included. So a commented template will be included with the system so people can see what they need to put in these specific spots. And there'll be additional information included in a extensive manual. So going kind of deeper into the contagion simulation module, this is the bulk of the code. We have these contagion parameters, things like number of iterations. You probably don't want to run a simulation just once. You want to run it 100 or 1,000 times. A set of infectious states. So in an SIR model, that's obviously I, but you might have a very complex model with several sets of infectious states, I1, I2, something like that. A simulation runtime. So SIR models will end eventually, but if you're in an SAS model, it might go on forever. You want to limit that runtime to 100 time steps or 1,000 time steps or something. And the random number generation seed, just for consistency among simulations. The graph, pretty standard, nodes, edges, and whether it's directed or undirected. The initial states set, which is just which nodes are in what state at the start of each simulation. So, first 10 nodes are in S, second 10 nodes are in I, or something like that. And finally, the models and transition rules, which I have included together because one kind of makes up the other. So you have your set of states, SIR or SIS, things like that. You have a set of allowed transitions, so S to E to I to R in an SER model. So nodes cannot transition in any other way than exactly what you specify. A set of transition rules, whether they be discrete, threshold, or etc. We'll go expand more on those later. And then each of those transition rules has parameters to be customized to whatever set of simulations you want. Diving a little deeper into the transition rules, this is how the EoN++ system decides how each node is going to change state. There's currently 5 rules implemented. We're going to implement a few more. And if anyone requests a new rule be implemented, it's not too difficult to implement a new one. But the 5 we currently have are discrete, where a node will remain in a state for an exact number of time steps. So someone might be infected for exactly 5 time steps and then move on to a recovery state. There's a probability transition where at every time step, there's a chance that the node changes state. So maybe instead of remaining infected for 5 exact time steps, there's a 75% chance at every time step that the node changes from I to R. There's threshold, where each node looks at its infected neighbors, and if the number of infected neighbors reaches a certain amount, then the node will change states. So if a susceptible node has 10 infected neighbors, then it'll change states to infected. A combination of the last two, threshold and probability, can have it such that it will look at the number of infected neighbors and then will have a chance to change states. So if 10 neighbors are infected, it has a 50% chance to change states. And then finally, linear threshold, where instead of just looking at the absolute number of neighbors, each edge has an edge weight of how, or that gets summed up together to form the threshold. So if a node has 3 edges, one might have a weight of 0.7, another might have 1 and one of 2. That would end up being 3.7. So all of these have parameters that can be changed on a per node or per edge basis. So each node in a system can have a different transition rule and parameter from all the other nodes. So your first node might have a discrete 1 time transition on the transition from S to I or something. And then your second node might have a probability transition from S to I. And each of those can have different transitions from I to R as well. So it's completely heterogeneous. You can kind of do whatever you want, make your model as complex as you want. I'm going to be demoing this at a high level. So we're going to look at a very simple contagion simulation with 5 nodes. At the start of the system, node 0 is going to be infected here. And we'll watch as it infects the rest of the system, except for node 2, which is recovered, so it won't be infected. This is an SIR simulation. So at time 1, you can expect node 1 to get infected. At time 2, node 0 will recover, and node 3 will be infected. And then at time 3, all 3 nodes 1, 3, and 4 will be infected. And then that'll be the end of the simulation because I didn't want to continue it any longer. So this is generally what we're going to look at. This is what a general configuration file looks like for the contagion simulation code. It's pretty extensive, so I won't go deep into the details, but when we provide this code, there will be a set of instructions that go into each and every one of these lines and describes what is there and what should go there and how many, what there should be. So it has 2 sections, a files section and a parameters section, files for reading in the different files that the simulation needs, and then parameters for setting up the simulation itself. This contagion runs off of this graph file, which is just an adjacency list representation of the graph that I just showed you. NetworkX can generate these pretty easily and directly out into this output exactly. So this is very simple to generate if you have a NetworkX object. A set of initial states is in just a space separated list like so. You have your nodes and what states they start out in. So this file represents this initial state set. And finally, we have a node properties list. Again, won't go incredibly deep into this, but you can see that you have your listed nodes, your allowed transition, and the rule that this transition happens upon. So for node 0, it has an allowed transition from S to I. That happens in a discrete time step of 1. And then it also has a transition from I to R. This happens in exactly 2 time steps. So pretty simple. Everything else just has a transition from S to I, and that's it. So they can only go to state I. So we will run this real quick. I'm just going to copy and paste this command in so see it. So it's a pretty typical command line invocation, Python, the name of the code, a config file switch, and then the link to your configuration file. The configuration file also specifies where the file is going to be output. So it'll run. We'll let you know that the termination was good. I'll zoom in a little bit here so you can see. So there was a good termination, and it gives a time analysis of how long it took. And we put the output right here. So this is the raw output file. It has a list of 7 columns. The first is the model. I didn't use multiple models in this particular simulation, so that just defaults to a 0. And in the future, we'll have a switch to remove these first 4 columns in case you're not interested in having them. But the next 3 columns just describe where the files it was drawing from are found. So this is the path to the graph file that it was reading from, the path to the initial conditions file, and this 4th column is actually which iteration the simulation was on. I ran 2 simulations and they are indexed by 0. So you can see that these are the set of iteration 0s, and then this is the set of iteration 1s. And so it's difficult to read because it's at the edge here. So I'll bring it more to the middle. Right here is the list of state changes. Each time a line appears as a node changing state at a certain time step. So the first 5 lines are going to be the initial state set, node 0 in state I, node 2 in state R, everything else in state S, which is exactly what we were seeing here. And then you can see that at time 1, node 1 changes to state I, which is exactly what we were expecting. And the rest of the nodes follow suit. Node 0 recovers at time 2, node 3 gets infected at time 2 as well, and then at time 3, the last node gets infected. Because this is a non-random model, it's exact, discrete is exact, nothing will change. Both of these iterations are exactly the same, but in a probabilistic model, this will not be the case. So this is the raw output that will eventually get input into the data analysis portion of the code, which I'll go into next. A little bit longer, more on making models with transition rules. You're kind of limited by your imagination a little bit. There's no real limit to the models you can make unless the transition rule you need isn't implemented. So lots of popular models can already be implemented in EoN++ without any additional code to be written, just the usage of the transition rules, state transitions, and the input files. I've already commented on SIS and SIR models. You just have state transitions as S to I and I to S, or S to I and I to R, and then you'd have in a real SIS or SIR model, in the same way that Epidemics on Networks library does it, you just have probability for both of those transition rules. You can also change up these set of rules and have an independent cascade model with the same state transitions as SAR, but instead of a probability on the transition rule for R, you have a discrete time of 1. But that's just a pretty simple 1 keyword change in the input file, and you can set your SIR model into an independent cascade model. You're not limited by states either, so you can easily expand an SIR model into an SEIR model if you wanted, or just create a SE, E2, I1, I2 model if you wanted. So all of these can just be implemented. There's no limit on number of state transitions. And then other types of models like deterministic and probabilistic threshold can be implemented very simply with just threshold and threshold probability transition rules. Again, this is a prettier version of the output that I showed you in the code. The 7 columns here with the name of the model, the graph file that was being looked at, as well as the initial conditions file, which iteration it is, the time, the node, and the state change, each on its own line. All the data is here, and what we'll move on to next is the data analysis code. So that was an example of the raw output. The data analysis module will take in a user input of model, graph, and initial condition selection, as well as a state of interest, and process it into a more useful output for analyzing. This is pretty simple. I'll go and show the configuration file, but the output goes from the raw output we were looking into earlier into an output of a list of times and how many nodes are in that state at each time per iteration. So there will be the number of columns equal to the number of iterations, and then at each time will be listed the number of nodes that are in each state at that time. So for example, you might be interested in state I in that particular model. For a very small graph, you might have this list where at time 0 in iteration 1, as well as everything else, this would be reading off of your initial seed set. You might have 1 in each iteration, but then it would change over each other iteration. And then by time step 3, maybe they all recover. So we'll very quickly look into what that looks like. So the configuration files are a lot less dense than for the data analysis code than the contagion simulation code. It has the name of the data file, which was the one we just created, the model name, graph name, and initial conditions name that you're interested in, state of interest, and then the output file name. I'll write 3 of these to get an analyzed file for each of the 3 states that we have, and then I will run them all. So similar invocation here, Python, the name of the Python code, configuration file path, and similar output on the command line of the time and whether the termination was good or not. So This creates 3 output files that list the state of interest that you selected and then the data. So each time should go from 0 to the end time. And then this had 2 iterations. So there's 2 other columns of where the data was at that point. This isn't particularly interesting because it's a 5-node graph, but that's what you have. This output here will get fed directly into the plotting code. So the plotting code will take in this processed output and matplotlib parameters. A lot of you are probably familiar with matplotlib. It's one of the primary Python plotting libraries. So it'll take those in and a list of plot types. Right now we support 5 of them. We'll expand that to a few more before this code gets published. So if you want an error bar plot, a scatter plot, a line plot, or etc., those are all supported. For those of you that don't know matplotlib features, with extensive use of matplotlib, you can make a plot look exactly however you want to. And I expose, I would say, a large portion of those to the input file to be set. So most plots that you would want can be created via the input file without writing any additional code. So this includes changing the colors of the lines in the data, customizing all the text on the plot, the legend, the axis names in the title, all the font sizes. It supports the different types of plots I listed, different output formats, JPEG, PNG, EPS if you're submitting to a paper, PDF if you need that. And then there's more that I won't go into, but they're all supported. And so this output gets set into just a plot. A very simple 100-node simulation might have a plot that looks like this for a line plot. You have your legend, your time on the x-axis, number of nodes on the y. And so I set all of this text here manually, all the colors and the types of the font sizes. All of that is set manually. This is the same plotted data, but this is an error bar. And instead of having the number of nodes, instead it's a normalized plot where it's showing the fraction of the whole. So you can see the standard error of the data here. I'll show an example of that. So this is a plot configuration file. The data files that we presented get set in here. The names on the legend, the colors, and other parameters that I won't go into because they're complicated. And then the plotting parameters are all done here, where you can set your font sizes, your text, scales, X limits, Y limits, and so on. After setting all of that up, you can just run an invocation of the plot code, and you will get 3 plots. So these aren't the most exciting plots in the world because they're plotting 5 size model, but you can see that the error bar shows no standard error because the 2 iterations were exactly the same, and that at each state, 1 node was infected during that time step, and 1 node recovered at time step 0, 0 nodes covered at time step 1, and 1 node recovered at time step 2. This is the same data, but a little cleaner because it's a line plot. No need to show standard error because there's no variation in the data. And this is a scatter plot in case you want that. So obviously in a more complex model, you'll have points that aren't on top of each other and the graph will look a little more filled out. That about sums up the extensions and modifications I've made to EoN in the system. So now we're going to get onto the kind of nitty-gritty details. We have not parallelized the code yet. So this is serial code runtime for 100 iterations. The bottom here is a log scale. So this is graph of size 10, 100, 1,000, 10,000, and 100,000. So this is roughly 3 hours for 100 average degree graph to run the contagion simulation code. We're intending to cut this down by parallelizing it, but this is kind of where we're at. No, models of size 1,000 or so will run in under an hour, under 10 minutes even. Going on what we're going to do in the future. So for the contagion simulation code, the main priority right now is parallelization. We're going to have 2 methods to do that. One is just splitting iterations across Slurm jobs. So instead of 1 Slurm job handling 100 iterations, we'll just have 100 Slurm jobs. This is kind of very manual parallelization. And then the other type we'll have is each iteration running in its own thread. So that will be submit to the parallel core on Rivana, where that can be parallelized that way. And then, as I mentioned earlier, we're going to submit some more transition rules. One is that right now threshold looks at every single infectious state, but it's possible that certain models might have it such that threshold model only looks at a certain subset of those. So we'll have a threshold transition rule that only looks at a specific set of specified states per node rather than all of them. And then as any additional transition rules are requested to make other models that people might want, we'll implement those. And finally, so right now the data analysis code shows the number of new nodes entering a state at any time step. We're going to expand that out to also include the cumulative numbers of nodes in each state at each time. When this is all delivered, the source code will all be there, including the contagion simulation, data analysis, and plotting module. We'll have verification cases, including examples, expected results, and scripts to run those. So if you download it onto your machine, you can run those scripts and make sure that it's running on your machine the same way it ran on mine or on Rivana. And then we'll have extensive manuals, including slides, detailed instructions, and then examples. And so all of this will be accessible to let people kind of play around with it and learn how to use it. So, any questions?
Well, folks, let me just mention that Josh has already prepared a manual. So if you like to see it, we can certainly give you access. It's an overleaf document right now. Okay, we can give you permission to read the document so that you can take a look at all the facilities and more detailed explanations for the various models and so on. Are there any questions for Josh? Please feel free to email Josh also. If something is not clear, please feel free to email Josh or me or Chris or all three of us, whatever is convenient here. Okay, I hope people will start using EoN++. It's a very nice system. From what I've seen, it looks like, there's many capabilities beyond EoN.
Yeah, so that's part of the plan to put it on GitHub repo that people can access. And so if they prefer to use it on their own, like you said, they can.
Josh, that was a very nice presentation. If people don't have any questions, we can end the seminar right now. Okay, but as I said, if you have questions, please feel free to ask Josh.
Okay, thanks everybody for coming.
Thanks again, Josh. Okay, very nice job. Really enjoyed it.
Thanks a lot, Josh.
Right.
Yep.
Really
Really
nice job. Okay,
Thanks,
bye.
Josh.
Have a good night.